Okay, we're talking applications of geometric vectors. Applications of geometric vector addition. All right, so we're going to do this question. It's like a displacement question. So in an orienteering race, you walk 100 meters east. Let's draw that with our directed line segment. So we'll say that's 100 meters in the east direction. Then you walk north 70 degrees east for 60 meters. So that would look like, you know, if that's north, which it is. I'm not really like amazing at drawing these to scale, but it's nice if you can draw them somewhat accurately. Okay, that's 60 meters. I know this angle would be 70, and this one would be 90. So the angle in between the two vectors there would be 160 degrees. And I'm looking for how far I am from my starting position. So that's my displacement. So I'm adding these vectors. See how I place them head to tail? And then I connect them. And sorry, that was like a terrible diagram here. This would be my resultant vector. Just gonna, oh my gosh. Sorry, I'm just gonna maybe choose a thinner pencil and try to fit that all in there. Sorry, really quick redraw here. Okay, just pretend that degrees isn't there. Okay, so this whole thing is 160. Okay. All right, so I'm trying to find the resultant vector. And I also want to know this angle here because I want to know what bearing I'm walking at. And since this is my starting position and I'm heading this way. Okay, so it looks like cosine law is going to help us get the magnitude of the resultant vector because I've got the two sides and the angle in between. Okay, so I'm going 100 squared plus 60 squared minus 2 times 100 times 60 times cos of 160. Square root that whole thing, and you'll end up with a number around approximately 157.7 meters. So that's my resultant vector, 157.7. Now I want to find out what direction I'm going. So I'm going to use sine law for that. So sine theta over, what side is across from that? 60? Yes. And then sine 160 over 157.7. Or you could be more accurate than me if you want to. And I think if you solve that ratio, you'll get around 7 degrees. Something like that. We're just rounding to the nearest degree here. I think that's good enough. So 7 degrees. So I could describe my walk as going east 7 degrees north. Or if I wanted to get it from the north, I know that this would be 90 minus 7. So 83 degrees. So I could say that my displacement was 157.7 meters north, 83 degrees east. And that's that. Next question. An airplane is flying at a speed of 500 kilometers per hour and a heading of 40 degrees. All right, I'm going to just draw these as I talk about them. Okay, so on a heading of 40 degrees, so that's going to look like this. Probably longer, but anyways. It's going 500 kilometers per hour. This is my airplane. That angle is 40 degrees. Okay, that's what my airplane looks like. Now let's draw my, the wind. Let's see what happens here with the wind. Okay. The wind is blowing okay, let's just work on that language there. From a bearing, that sounds better. So check out this word from, that's key. From a bearing of 120. All right, so let's find a bearing of 120. So bearings, they start at north and they go clockwise. So 120 is going to be down here somewhere. And since it says from, that means it's coming from that way and going that way. So that whole angle there is 120. If I do 120 minus this 90 degree angle, I know this angle is 30 degrees, which is helpful. So actually my wind is going like this way. So using opposite angles, that would be 30 degrees. And it's going 150 kilometers per hour. And since it's from a bearing of 120, it's coming from that way and it's going to that way. So that's a bit confusing. Now we're looking for the ground velocity of the airplane and the direction of flight. So the airplane is the purple diagram here, but the wind is going to push it. So it's going to end up going slightly more west than it is, right? It's got the... and it's going to slow it down a little bit. So let's add these vectors together to find out what the ground velocity of the airplane is. So we're going to add the velocity of the airplane and the wind and figure out what the ground velocity of the airplane is. Okay, so I'm going to put these vectors head to tail. Okay, so I'm going to start. You could do this a couple different ways, but I'll just do it one way. I'm going to start with my airplane. I probably should have drawn this farther down, but oh well. Okay, that's my airplane. You know what? Sorry, I just want to move that down a little bit because I feel like I'm going to run out of room. Okay, cool. I grabbed the wind speed there with me. Okay, so here's my airplane. That's 500 kilometers per hour. That angle is 40 degrees. Now I'm going to draw my wind so that it's starting here. So my wind is at an angle of 30 degrees. So this is going to be my wind. That's 30 degrees. That's 150 kilometers per hour. Okay, and then my resultant vector is going to be like the start to the end here. So that is going to be my resultant vector. Let's figure out some missing angles. So I know since this angle here is 40 degrees, using parallel lines, like I know this line is parallel to this line. So I know that this angle down here would be 40 degrees also, because alternate angles. And since these two angles add up to 90, I know this would be 50 degrees. So now I can tell this whole angle in here would be 80 degrees. Okay, and that's all I really need, because now I can do cosine law to find the magnitude of the resultant vector. I'm just going to shrink it so I can see what I'm doing here. So magnitude of the resultant vector is going to be 150 squared plus 500 squared minus 2 times 150 times 500 times the cosine of 80 degrees. And once I calculate that all out using my calculator, I end up with approximately 496.440. Just have a ton of decimal places for this one for some reason. Okay, so that's my resultant vector. So that's the speed of the plane with respect to the ground. And now I need to know the direction. So I need to get this angle or something. So I'll try to get this angle down here using sine law. Ooh, that's probably a bit bright. Let's use red. Okay, so I'm going to do sine theta over 150 equals sine 80 over 496.440. And I don't have my calculator. I think it's about 17. But I just need to calculate it. It's cutting into my time. Sine 80 over 496.440 times 150 inverse sine. Yeah, 17. So that's 17 degrees in here. And since I know this whole angle is 40, I can do 40 minus 17 to get this angle, which is 23. Sorry about this ridiculous noise in my house. Okay, so the resultant vector of the airplane is 496 6.4 kilometers per hour, and it's going in a direction north 23 degrees east. So you can see the wind kind of slowed it down, and it was going north 40 east, so it's kind of pushing it towards the other direction. Not as east. All right, so that's how you add geometric vectors, and these are application questions because they're like, I don't know, real life, like airplanes and walking. And it's just, you know, the best way is just, oh my gosh, sorry, just to set it up like this and place the vectors tip to tail, head to tail, same thing. Okay.